Hello and welcome to today's video. In this video we're going to talk about convergence of series once more. Specifically, we're going to investigate a few criteria that will help us to determine whether a series converges. To do that, we first have to define the notion of absolute convergence, and then we can list the criteria that we're going to use. So this is titled Absolute Convergence and Convergence Criteria. And we'll start with the definition of absolute convergence right away. So let's say we have a series of the form sum over some ak, k from 0 to infinity. Then this is called absolutely convergent if the series over the absolute values of the ak also converges. So the series is called absolutely convergent if the series given by the sum from k to infinity over the absolute values of the ak converges. And as a quick remark, if a series converges absolutely, then of course the original series will also be convergent. So a series that converges absolutely is also convergent. And now let's have a look at criteria that enable us to see whether a series is absolutely convergent or not. Now, these criteria will not work in all possible circumstances, also because there are series that are not absolutely convergent but still convergent. And even for the absolutely convergent series, these criteria will not detect every possibly convergent series. So there are still cases where you cannot use these criteria, where they will return a result that says undecided using this criterion. And then of course you'll have to employ other means. But in many cases, these criteria will help you out. So we'll first list them, explain them, and then we'll see a few examples. So for all of these criteria, we'll consider a sequence AK, indices in N0. Let that be a sequence, and we'll always consider the series defined by the summons AK. So then the following hold. And the first criterion that we're looking at is the so-called comparison test. Now that is a very powerful criterion, but also one that is not easy to apply. The idea here is to compare the sequence AK to a different sequence BK, where you already know that the series over the BK converges. And then if the AKs are all less or equal to the BKs, or the absolute values are less or equal to the BKs, then you can infer that the series of the AKs will also converge. That is the idea of the comparison test. So if there is a sequence BK and 0 such that the following two conditions hold. First, the absolute value of each AK is less or equal to BK. And that's true for all K in N0. And the second condition is the series over the BK converges. And you can see from the first condition that, of course, the BKs have to be non-negative. So this series also converges absolutely because there are no negative BK. So these two conditions are satisfied. Then the comparison test tells us that the series of the AK also converges, and it even converges absolutely. So what we have is, in a way, that the AKs are sandwiched between 0, the AK, absolute values of the AKs are sandwiched between 0 and the BKs. So this is kind of a sandwich theorem, and actually that would be necessary to prove this argument here. The second test is something that's often easier to apply, but it's also not that powerful. That is called the ratio test. We first discuss a very strict variant of the ratio test. I'll discuss easier cases in just a minute. So, simple but strict variant is, if the AKs are non-zero, for all K in N0, and if there exists some Q in R, such that, and now here comes the test. What you do is you take AK plus 1 and AK and you compute their ratio, and more precisely the absolute value of that ratio. And that needs to be bounded by Q, and Q needs to be strictly less than 1. For all K in N0, once again, then the series over the AK, K from 0 to infinity, converges absolutely. Please note that you need a strict inequality here. So if the ratio is equal to 1, then you cannot apply this test. Also, there is a negative test as well. I'll discuss this in a minute. If the ratio is strictly greater than 1 for all K's, then this test will also say that the sequence diverges. But if it's strictly equal to 1, then it could still converge, but the test is inconclusive. Yeah, so then ratio test just doesn't help, and you'll have to try some other means of inferring convergence or divergence of that series. Also note that is in this version here, we need this ratio to be less than 1, strictly less than 1, for all K in N0. And this is something that can be relaxed, and again, I'll talk about that in a minute, because it also applies to all the other tests. So let's first list the third test in that row here. That is called the root test. The root test is, in theory, more powerful than the ratio test, but it's also harder to apply in many circumstances, not in all. Sometimes the root test is easier to apply, and of course that depends on how the AKs actually look like. So let's have a look at that. If there exists, again, such a Q in R, such that the following holds. Now for the root test, we take the kth root of the absolute value of a K, and that kth root needs to be less or equal to the constant Q, which is in turn strictly less than 1. So again, please note there's a strictly less than 1 here. equality doesn't cut it. And again, we need that for all k in N0. Then the series over the AK converges absolutely. So these are the three tests that we will be learning about in this section here. And as I said, a couple of remarks is in order before we actually apply them. Now, for all tests, it is sufficient that the conditions hold for large enough k. So you can always dismiss smaller k's, a finite number of smaller k's. And that means if the conditions eventually hold, if the k's are large enough, but then from some point on for all k's, that will be sufficient. That basically reflects the idea that you can change any sequence in finitely many places without altering convergence properties. You might, of course, change the actual value of the limit, but the fact whether a sequence converges or not is not changed by finitely many alterations of that sequence. So, for all tests, it is sufficient that the conditions hold for large enough values of k, meaning there is an n in N0 such that the conditions hold for all k greater or equal to capital N. That's the precise formulation here. In other words, small k's don't matter. You only have to care about large enough k's, if that helps in any way. And this idea is taken a step further in that second remark here. So this condition can also be tested by taking limits in many cases. So specifically for the root and the ratio test, the following is true. If the limit of the AK plus 1 to AK ratio in absolute values is strictly less than 1, that means the series over the AKs converges absolutely. If that limit is strictly greater than 1, that means that this series diverges absolutely. So the series of the absolute values diverges. It does not exclude convergence, but it does exclude absolute convergence. And if the limit is equal to 1, that means the test is inconclusive. So you don't get a result, you have to try some other way. The limit, of course, is for k to infinity. And the same is true for the root test. You can also take the limit there. So if the limit k to infinity of the kth root of the absolute value of ak is less than 1, that will mean the series over the AK converges absolutely. If that limit is strictly greater than 1, that will mean this series over the AKs, or the absolute values of the AKs, diverges. And third option, if it's equal to 1, that can also happen, of course, then again, the test is inconclusive. So if that happens, you'll have to try some other way of proving or disproving convergence. And again, notice we always have strict inequality here. So if the ratio is equal to 1 or if the limit is equal to 1, that doesn't tell you anything. And also here in the stricter formulation, you have this constant q that is strictly less than 1, and all these expressions have to stay below q. So it doesn't help if they are strictly smaller than 1. They have to be below some constant, which is in turn strictly smaller than 1. If they approach 1 and get infinitely close to 1, that does not help. Yeah? Then again, the limit is 1, and the test will be inconclusive. Okay, let's have a look at a few examples to see how you can apply these tests. First one. Part A, let's have a look at the series defined by the summons 2 to the power of k over k factorial. Now for these, we can try a ratio test. And the AKs are obviously equal to those summons 2 to the power of k over k factorial. So if we try the ratio test here, we get AK plus 1 over AK in absolute values. Obviously, the AKs are non-negative anyway, so we can just forget about the absolute values in this case. AK plus 1 is 2k plus 1 over k plus 1 factorial. So this is AK plus 1. And then we have divided by AK, so we multiply with the reciprocal value here, and that is k factorial over 2 to the power of k. So this here is 1 over AK. Now what you can see is 2 to the power of k plus 1, that is equal to 2 times 2 to the power of k. We just leave the k factorial. Then we have a 2 to the power of k here in the denominator, and we also have this k plus 1 factorial, and that can also be split. That is the same as k plus 1 times k factorial. So a number of things cancels out, and that is where the power of the ratio test comes from. If you have factors where a number of things will cancel out, then the ratio test often helps. So in this case, the 2 to the power of k cancel out, and the k factorial cancels out. So we are left with 2 over k plus 1. And if we now take the limit of that, as k goes to infinity, you'll find that this goes to 0, and 0 is strictly less than 1. So that means that series converges by the ratio test. So the 2 to the k over k factorial, that converges absolutely by the ratio test. And as usual, if you apply one of these tests in an exam, please be sure to mention which test you're trying to apply. Because if you make a mistake somewhere, then at least the corrector will know your intentions, and maybe you'll still get a point for those. Finally, let's also see an example for the root test, so part B. Let's consider the sequence from 0 to infinity, 2 to the power of k, divided by 4 plus minus 1 to the power of k, and this expression again to the power of k. So here we have some alternating part in that sequence as well. But what you'll notice is, of course, that we have a power k in both numerator and denominator. And that, of course, makes it easy to compute the kth root of that expression. So we're going to apply the root test here. So we apply the root test with ak being equal to 2 to the power of k over 4 plus minus 1 to the power of k, and all that to the power of k. And well, the following happens. First, we'll have to discuss the sign of ak. So can ak become negative? The only negative component is this minus 1 to the power of k. So that alternates between plus and minus 1. So the denominator is 4 plus minus 1 to the power of k. This alternates between 4 minus 1, which is 3, and 4 plus 1, which is 5. So this is either 3 or 5 for all k. And that means we always have that ak is positive. And thus we can apply the root test right away. So the kth root of the absolute value of ak is equal to the kth root of the ak's. And that kth root, well, that is simply 2 over 4 plus minus 1 to the power of k. So that 1k stays in here. And now there's two possibilities. Well, that is either 2 divided by 3 or 2 divided by 5. It will be 2 divided by 3 if the minus 1 to the power of k is negative. So if the k is odd. So we have 2/3 for odd k, and it will be 2 over 5 for even k. In both cases, this ratio is strictly less than 1. And that means this series here does indeed converge. And it converges absolutely by the root test. Now please note, these criteria give us a means of determining whether a series converges or maybe diverges. In many cases, what it does not give us is the limit. So we know that these series here converge, but we still don't know their limit. And actually computing that limit might be a very hard task of their own. There's often no easy way of getting to that limit, even though we might know that the series converge. So this concludes these criteria for absolute convergence. We'll also discuss a criterion for series that might not absolutely converge but still converge. But again, in many cases where these criteria don't apply, you just have to use your creativity to find out whether the series converges and maybe even get the right limit value. I'll see you in the following videos then.